something changed in the data. Not loudly, not with fanfare. It changed the way a crack appears in ice before the whole surface gives way, quietly, incrementally, and then all at once obvious to anyone paying close attention. On the 6th of March, 2026, a paper landed in Geophysical Research Letters that stopped climate scientists mid-conversation. Not because it confirmed warming. We have confirmed warming for decades. It stopped them because of what the numbers implied about the rate, about the direction of travel, and about the uncomfortable distance between what our best predictive models told us should be happening and what the instruments are actually recording right now. Let me give you the core of it before we go any further. Grant Foster and Foster and Rahmstorf, two researchers with long, serious track records in climate data analysis, published a study that used refined statistical methods to strip the global temperature record of everything natural, every El Nino pulse, every volcanic cooling episode, every fluctuation tied to the 11-year solar cycle. They removed all of it, as cleanly as current methodology allows, to isolate the one signal they were hunting, the underlying human-caused warming trend, the anthropogenic fingerprint running beneath all the noise. What they found in that residual signal, in that temperature record after nature had been mathematically subtracted, was acceleration. Not a flattening, not a steady linear climb, an acceleration, confirmed at over 98% statistical confidence. The last decade warmer than any equivalent period in the entire instrumental record, and warming faster at its end than at its beginning. Stay with me here, because this is where it gets genuinely strange. Climate models, particularly the generation of models that fed into the 6th assessment report of the Intergovernmental Panel on Climate Change, are extraordinarily sophisticated tools. They encode the physics of the atmosphere, the ocean, sea ice, land surface processes, and the carbon cycle into computational frameworks that run on some of the most powerful supercomputers on Earth. These are not back-of-envelope estimates. They are the product of decades of coordinated international science involving thousands of researchers. And those models did not predict this. Not at this magnitude, not at this timing, not with this degree of statistical certainty arriving this early. The observed acceleration in the residual anthropogenic signal outpaces what the central estimates of those models projected for this period. Think about what that actually means. It means we stripped out El Nino, we stripped out volcanic aerosols, we stripped out solar variability, and what was left over, the signal that can only be attributed to human forcing of the climate system through greenhouse gas accumulation, is steeper than the sum of our best quantitative estimates of human forcing should theoretically produce. The inputs going into the system, primarily carbon dioxide now at roughly 425 parts per million in the atmosphere, methane and nitrous oxide, the accumulated radiative forcing of 2.5 centuries of industrialization, those inputs are well measured. They are not the mystery. The mystery is the output. The planet is responding to those inputs more aggressively than the physics as we have encoded it predicts. That is a sentence worth sitting with. We are not talking about a model being slightly off at the margins. We are talking about a statistically robust 98% confidence level signal, showing the Earth heating faster than our most comprehensive predictive framework said it would. In science, when your measurements consistently exceed your model's predictions, the correct response is not to dismiss the measurements. The correct response is to ask what the model is missing. And right now, that question does not have a single clean answer. That is what makes this paper genuinely significant and genuinely unsettling in a rigorous data-grounded sense. Here is where it gets interesting on a methodological level. Before the 2026 Foster-Rahmstorf analysis, the unadjusted raw global temperature record had already been whispering about acceleration. Researchers looking at raw surface station data and satellite-derived tropospheric temperatures could see the trend bending upward. But here is the problem with raw temperature data. It is extraordinarily noisy. The El Nino event of 2015 and 2016 drove global mean surface temperatures to record levels for reasons that were substantially natural, a massive release of heat stored in the Pacific Ocean into the atmosphere. Then the La Niña cooling that followed pulled temperatures back. Then the El Nino of 2023 and 2024 hit with comparable force, again spiking global means. These enormous swings, legitimate and natural in their proximate cause, acted like static across a radio signal. They were loud enough to push the apparent acceleration in raw data just below the 95% confidence threshold that science conventionally treats as the minimum standard for a claim to be considered statistically robust. Loud enough to let skeptics point at the noise and say the signal is not there. Foster and Rahmstorf's contribution was to develop regression modelling precise enough to turn that radiostatic down, precise enough that what remained was not ambiguous. But here is the cliffhanger embedded in their own results, the thing that the paper raises without fully resolving, the question that I want to carry through the full investigation we are undertaking here. When you subtract every natural oscillation you can measure, every forcing term you can quantify, and the residual is larger than your forcing inputs predict, you are left with one of two possibilities. Either your measurement of the forcing inputs is incomplete, meaning there is a source of warming you have not fully accounted for, or the system's response to the forcing you have measured is being amplified by a mechanism that your models are not adequately representing. A feedback, in other words. Something that takes the warming already in motion and multiplies it. Something that may have already engaged quietly in the background, in the ocean heat ledgers, in the cloud behavior over the subtropical Pacific, in the frozen soils of Siberia, in the slowing circulation of the North Atlantic. Something that was always predicted to eventually kick in, but was projected to kick in later, at higher temperatures, further down the road. What if it is not further down the road? What if the acceleration Foster and Rahmstorf have now confirmed at 98% confidence is not the beginning of a trend that will emerge in the future, but the early observable signature of a feedback engagement that is already underway? And if that is the case, if some amplifying loop is already running inside the Earth system, then the next question is not whether we have a problem. It is how fast the problem compounds from here. The models failed to predict the acceleration we are already measuring. The rate of that acceleration is itself accelerating, and the mechanisms that could explain the gap between prediction and observation are not reassuring ones. Each of them, if confirmed, carries implications that extend well beyond temperature statistics and deep into the physical infrastructure of the planet's climate system. Ice sheets, ocean circulation, atmospheric water vapor, permafrost carbon stores, systems that have operated within certain boundaries for the entire span of human civilization. That is what is actually at stake in a research paper that, on the surface, is just about adjusting temperature data for natural variability. That is why this matters, and that is exactly what we are going to unpack. The story of how science actually works is rarely the story we tell in textbooks. In textbooks, a hypothesis is formed, an experiment is run, data is collected, and a conclusion is reached. Clean, linear, satisfying. The real process looks almost nothing like that. It looks like years of researchers staring at data that is almost telling them something. Data that keeps hovering just below the threshold of certainty, close enough to be tantalizing and far enough to be professionally dangerous to commit to. That is exactly where the acceleration story lived for the better part of a decade before the 2026 paper resolved it. And understanding why it took this long, why the signal kept slipping below the confidence threshold, tells you something fundamental about both the difficulty of what Foster and Rahmstorf accomplished and the nature of the problem they were solving. Start with the raw numbers, because the raw numbers are genuinely instructive in their ambiguity. Global surface temperature datasets, whether you are looking at the Hadcrut record maintained by the UK Met Office and the Climatic Research Unit, the GIS-Temp record from NASA, or the independently derived Berkeley Earth dataset, all showed the same general shape when researchers examined them through the early 2020s. Temperatures rising, records falling. The warmest years in the instrumental record clustering into the most recent decade with a consistency that went far beyond statistical chance. If you drew a trend line through raw global mean surface temperature anomalies from roughly 2000 to 2024, you would see warming. Unambiguous, robust warming. What you would not see, at least not with the statistical clarity required to make a scientific claim, was whether the rate of that warming was itself increasing, whether the line was bending upward rather than simply extending upward. That distinction matters enormously, and the reason it was so hard to confirm in raw data comes down to two extraordinary events that landed in the middle of the measurement window like boulders thrown into a still pond. The El Nino of 2015 and 2016 was one of the strongest in the modern observational record. It drove global mean surface temperatures to levels that at the time were unprecedented, producing an anomaly spike so large and so sharp that it temporarily distorted every trend analysis attempting to look through it. Then La Niña conditions returned and temperatures cooled back somewhat. And then, almost as if nature were running a deliberate interference pattern, a comparably powerful El Niño emerged in 2023 and 2024, producing another massive spike, again setting records, again creating a short-term excursion in the data that swamped the longer-term signal researchers were trying to isolate. Picture trying to measure the precise height of a slowly rising tide while someone is intermittently dropping very large rocks into the water next to your measuring instrument. The waves are real. The rocks are real. But neither the waves nor the rocks are the tide, and separating them requires more than patience. It requires methodology. This is where the statistical problem becomes genuinely interesting. The conventional threshold for scientific confidence, the 95% confidence level, exists for a reason. It means that if you ran your analysis on random noise with no underlying signal, you would expect to get a result this extreme only 5 times in 100 such tests. That is a reasonable bar for most scientific claims, but it is a bar that raw temperature trend analyses kept failing to clear specifically for the acceleration hypothesis, not because the signal was not there, but because the El Niño spikes introduced enough variance into the dataset that the statistical test could not distinguish the acceleration from the possibility that the apparent bend in the trend was simply an artifact of where 2 unusually powerful warm events happened to land in time. The noise was not random in the way statistical tests assume. It was structured noise. Large correlated excursions driven by the Pacific Ocean's natural variability, and that structure made it unusually effective at obscuring the precise feature researchers were hunting. Earlier attempts to address this were made by serious researchers. Kevin Cowton and Robert Way at the University of York developed methods to account for gaps in surface temperature coverage, particularly in the Arctic where warming is fastest but station density is lowest. The Berkeley Earth Group independently constructed their own temperature record using a much larger network of station data and different interpolation methods. Both efforts improved the underlying dataset quality. What they did not fully resolve was the decomposition problem, the challenge of attributing each portion of the temperature signal to its specific forcing driver with enough precision that what remained after removal was a clean anthropogenic residual rather than a mixture of residual natural variability and human forcing blurred together at the edges. What Foster and Rahmstorf did differently in their 2026 analysis was to apply a more granular regression framework that treated the major natural forcing terms not as simple on-off switches, but as time-lagged, amplitude-varying contributors with measurable response profiles that could be fitted to the temperature data with greater specificity. The El Niño Southern Oscillation Index was incorporated with its appropriate 3 to 6 month lag on global mean surface temperature response. Volcanic aerosol forcing was entered using updated stratospheric optical depth measurements rather than older proxy reconstructions. Solar irradiance was represented using the most current satellite-derived total solar irradiance record. Each component was allowed to vary in its fitted coefficient rather than being assigned a fixed, assumed magnitude. This sounds like a technical refinement, and it is, but the consequence of doing it more precisely is that the residual after subtraction is correspondingly more precise, less contaminated by the fingerprints of the components you've removed. And when that residual was examined, the result was unambiguous. The anthropogenic signal, isolated from its natural context, showed a measurable steepening after 2014. Not a dramatic overnight shift, a gradual but statistically robust bending of the trend toward a faster rate of change. The acceleration that raw data had hinted at but could not confirm crossed the 95% confidence threshold, then crossed 98%. The result that had been lurking in the data for years, obscured by the noise of 2 historic El Niño events and the limitations of previous decomposition methods, became statistically incontrovertible. Now stay with me here, because this is where the analysis stops being a story about statistical methodology and starts being something considerably more consequential. The researchers were not simply confirming that warming is continuing. That was never in serious scientific doubt. They were confirming that the rate of warming, stripped of every natural explanation available, is increasing. And when you look at the magnitude of that residual signal, when you actually run the numbers on what level of anthropogenic forcing should theoretically be driving what level of surface temperature response given the radiative forcing from known greenhouse gas concentrations, a discrepancy emerges that the methodology itself cannot explain away. The residual warming signal is larger than the sum of measurable human inputs into the system would predict under standard climate sensitivity assumptions. After removing every natural driver they could quantify, the number that remained was bigger than the number that should remain, not by an order of magnitude, not by an amount that suggests fundamental physics is broken, but by a measurable margin, a margin that sits outside the uncertainty range of the forcing estimates themselves, a margin that demands an explanation. Something is taking the forcing signal and amplifying it beyond what the base physics of carbon dioxide and methane radiative transfer alone would produce. Something in the system is responding in a way that adds to, rather than simply transmits, the warming that human emissions are driving. The question of what that something is, and whether it has already crossed from a future theoretical concern into a present operational reality, is the thread that now runs through every piece of data this investigation is going to examine. The three pillars of natural climate variability that Foster and Rahmstorf had to dismantle before they could see the underlying human signal are each, individually, a measurement problem of considerable complexity. Together, they represent one of the most technically demanding decomposition challenges in observational climatology, and the way those three pillars interact with each other, the way pulling on one thread sometimes moves the others, is precisely where the analysis gets philosophically uncomfortable in ways that go beyond simple statistical mechanics. Start with El Nino, because it is the most familiar and in some ways the most treacherous of the three. The El Nino Southern Oscillation is tracked primarily through sea surface temperature anomalies in the central and eastern tropical Pacific, in a region designated Nino 3.4, which stretches roughly from the dateline to about 120 degrees west longitude and straddles the equator. When that region runs warmer than its long-term average by a defined threshold for a sustained period, it signals El Niño conditions. When it runs cooler, La Niña. The ENSO index derived from those anomalies is a reasonable proxy for the oscillation's strength, but it is not a perfect predictor of global mean surface temperature response. The translation from Pacific sea surface warming to atmospheric temperature at the global scale involves a lag. The atmosphere does not respond instantaneously. Heat moves from the ocean surface into the lower troposphere through evaporation, and direct contact circulates globally through atmospheric teleconnections, and the full global mean surface temperature response to an El Niño event typically peaks somewhere between 3 and 6 months after the ocean anomaly itself peaks. That lag is consistent enough to be parameterized, but its precise value varies from event to event depending on the spatial pattern and vertical structure of the ocean warming involved. When you fit an ENSO term to a global temperature record, you're not plugging in a fixed number. You're fitting a response curve with measurable uncertainty in both its amplitude and its timing. That uncertainty propagates into the residual. Volcanic aerosols present a different kind of measurement challenge. Large volcanic eruptions inject sulfur dioxide into the stratosphere, where it oxidizes to form sulfate aerosol particles that scatter incoming solar radiation and produce a temporary cooling effect at the surface. The magnitude and duration of that cooling depend on how much sulfur reaches the stratosphere, how widely the aerosol cloud disperses, and how quickly it settles out. The standard measurement tool for stratospheric aerosol optical depth, which quantifies how much solar radiation the aerosol layer is blocking at any given time, currently relies substantially on instruments like SAGE-3, the Stratospheric Aerosol and Gas Experiment, which operates aboard the International Space Station. SAGE-3 measures aerosol optical depth by observing solar and lunar occultations, essentially watching the sun or moon through the stratospheric layer as it rises and sets from the perspective of the station's orbit, and inferring the aerosol concentration from how much the light is attenuated. The instrument is excellent. Its coverage is not continuous. There are latitudinal gaps and temporal sampling limitations that introduce uncertainty into the reconstruction of the global aerosol field, particularly in the immediate aftermath of a major eruption when the aerosol distribution is most heterogeneous. The period that Foster and Rahmstorf were analysing was relatively quiet volcanically, compared to earlier decades. The eruption of Mount Pinatubo in 1991, for context, injected roughly 20 million tons of sulfur dioxide into the stratosphere and cooled global mean surface temperatures by nearly 0.5 degrees Celsius for 2 years. Nothing comparable happened during the acceleration period under study. The volcanic cooling terms in the regression were therefore modest in magnitude, which is good for isolating the human signal, but also means small uncertainties in the aerosol measurements can translate into disproportionate fractional errors in the volcanic contribution term. The solar component is in some ways the cleanest of the three to measure and the most interesting in what it rules out. Total solar irradiance, the raw power output of the Sun, integrated across all wavelengths as it arrives at the top of Earth's atmosphere, has been monitored continuously by satellite since 1978. The current primary instrument is TSIS-1, the total and spectral solar irradiance sensor aboard the International Space Station, which took over from the SOAR-CE satellite and continues its measurement record. What that record shows across the period of maximum warming acceleration is this: the Sun was not the driver. Solar cycle 25, the current cycle which reached its solar maximum around 2025, was modestly more active than the relatively quiet solar cycle 24 that preceded it, but it was not an anomalously energetic cycle in any historical sense. The amplitude of variation in total solar irradiance across a full cycle is only about 0.1% of the Sun's total output, corresponding to a forcing change of roughly 0.1 watts per square metre at the top of the atmosphere. That's a small number against the roughly 3 watts per square metre of additional radiative forcing from accumulated anthropogenic greenhouse gases since pre-industrial times. The Sun cannot explain what Foster and Rahmstorf found. The math simply does not support it. But here is where the solar picture gets more complicated than the clean instrument record suggests. A subset of the literature, peer-reviewed and credible though not representing mainstream consensus, has explored indirect pathways by which solar variability might influence surface climate beyond the direct irradiance mechanism. The most developed of these involves the hypothesis that galactic cosmic rays, high-energy particles streaming in from outside the solar system, can seed the nucleation of aerosol particles in the lower atmosphere, potentially affecting cloud formation. During solar maximum, the Sun's enhanced magnetic field partially shields Earth from cosmic rays, reducing their flux. During solar minimum, cosmic ray flux increases. If cosmic rays genuinely influence cloud nucleation at a rate that matters climatically, then solar activity could affect surface temperature through a cloud cover pathway rather than a direct irradiance pathway, and that effect would not necessarily show up in the total solar irradiance record at all. The experimental evidence for this mechanism, including results from the cloud experiment at CERN, shows that cosmic rays can enhance aerosol nucleation under certain conditions. The translation of laboratory nucleation rates into meaningful global cloud cover changes remains contested. The forcing estimates derived from this mechanism by its proponents are generally small, typically well below the threshold needed to explain the acceleration gap. But the important scientific point is that this pathway, if it exists at even a modest level, would represent a solar forcing term absent from the regression that Foster and Rahmstorf ran, because no satellite record directly quantifies it at the required spatial and temporal resolution. It is a known unknown sitting at the edge of the analysis. Now pull all three of these threads together, and something genuinely important emerges. Each of the three natural variability terms, ENSO, volcanic aerosols and solar irradiance, carries its own measurement uncertainty and its own modelling assumptions about how it drives surface temperature response. Foster and Rahmstorf's regression treats these three terms as statistically independent of one another. That independence assumption is standard practice and generally defensible, but it is not perfectly accurate. And the reason it is not perfectly accurate has implications that reach directly into the interpretation of the residual signal they isolated. Consider this carefully. The background sea surface temperature of the tropical Pacific, the thermal reservoir that fuels El Nino events, is itself rising due to long-term anthropogenic warming. There is accumulating evidence that as the mean state of the Pacific warms, the magnitude of El Nino events, their peak anomaly amplitude, may be increasing. If El Nino events are themselves growing more intense as a consequence of background warming, then the ENSO index used to represent and remove them from the temperature record is not a purely independent natural variable. It is partly a consequence of the very human forcing trend the researchers are trying to isolate. When the regression removes a larger ENSO signal from the record, it may be inadvertently removing some portion of the anthropogenic signal that has contaminated the ENSO amplitude. The tool for separating human warming from natural variability may be entangled with the human warming itself. That does not invalidate the analysis. It complicates the interpretation of the residual. It means the residual anthropogenic signal Foster and Rahmstorf measured, already larger than model predictions account for, may actually be a conservative estimate. The true underlying human force trend could be steeper still, partially masked by an ENSO correction that is itself inflated by the warming it is supposed to be removing. That is not a small methodological footnote. That is a structural challenge embedded in the very act of trying to separate what is natural from what is not, in a system where those two things have been interacting and feeding back on each other for long enough that they are no longer fully separable. The signal and the noise, it turns out, are not independent quantities, and that realization changes how we need to think about everything the data is telling us. Here is where the global story gets a local face. Numbers at planetary scale are genuinely difficult to hold in the mind. A fraction of a degree added to the global mean surface temperature anomaly sounds like a rounding error to anyone who has not spent time understanding what that average represents or how much thermal energy it encodes. So let me give you something concrete. Let me give you a city, a specific place with a specific history of weather records stretching back over a century, where what happened in the winter of 2025 to 2026 was not an abstraction and not a projection. It was simply the measured daily temperature, recorded by instruments. The Hong Kong Observatory has been operating for longer than most currently living people have been alive, and what those instruments recorded was extraordinary in the most technically precise sense of that word. The mean temperature for that winter season across Hong Kong came in at 19.3 degrees Celsius. That is the number. Write it down if you like, because it is going to need some context before its full weight becomes apparent. The climatological normal for Hong Kong winter temperatures, calculated across the reference period from 1991 to 2020, sits at approximately 17.3 degrees Celsius. The departure from normal is therefore exactly 2 full degrees Celsius. That is not a marginal exceedance. That is not a record broken by 1/10 of a degree, the kind of narrow margin that statisticians caveat carefully. 2 full degrees above the established baseline for an entire season is a departure of a magnitude that, in the context of regional climatology for a subtropical coastal city, represents something that sits well outside the distribution of normal variability. But the temperature anomaly alone is only part of what the Hong Kong data is telling us. The more striking statistic, the one that points most directly toward a structural change, rather than a lucky draw from natural variability, is the cold day count. In Hong Kong, a cold day is formally defined as a day on which the daily minimum temperature drops below 12 degrees Celsius, a threshold that reflects the subtropical climate's version of meaningful winter chill. Historically, averaged across the observational record spanning more than a century, Hong Kong experiences something in the range of 14 cold days in a typical winter season. In the winter just measured, there were 5 cold days against a historical expectation of roughly 14. That is not a subtle shift in the tail of a distribution. That is a near disappearance of a seasonal feature that has characterized the regional climate for as long as continuous records exist, and it places the season as the 3rd lowest cold day count in the entire century-plus observational history of the observatory. Stay with me here, because the mechanism behind this is not random. Hong Kong's winter climate is fundamentally governed by the East Asian winter monsoon. This is a large-scale atmospheric circulation system driven by a pressure gradient between 2 enormous features. The Siberian High over the interior of the Asian continent to the north, which is a massive dome of cold, dense air that builds over Siberia as the landmass radiates heat to space through the long winter nights, and the relatively warm western Pacific Ocean to the south and east. The temperature difference between those two systems, between the frigid continental interior and the warmer ocean, generates a pressure gradient that drives cold air southward and eastward out of Siberia and across the Korean peninsula, mainland China, and eventually into the subtropics where Hong Kong sits. When that flow is strong, cold surges push southward, with enough momentum to drive temperatures in Hong Kong well below the cold day threshold. When that flow weakens, the cold air masses either fail to penetrate as far south, or they arrive diluted by mixing with warmer subtropical air along the way. Now consider what has been happening at the Siberian end of that pressure gradient. The Arctic and subarctic regions have been warming at approximately 2 to 3 times the global mean rate, a phenomenon known as polar amplification that emerges from a set of reinforcing feedbacks, including sea ice loss, which reduces surface reflectivity and allows the dark ocean to absorb more solar energy, and changes in water vapour and cloud distribution at high latitudes. As the Arctic warms faster than the tropics, the temperature contrast between the pole and the equator decreases. That contrast is precisely what drives the strength and southward extent of cold air outbreaks in winter. A smaller temperature difference between high and low latitudes produces a less vigorous circulation. The Siberian high still forms, but its pressure gradient against the Pacific is diminished. Cold surges still occur, but they are weaker and less frequent. What happened to Hong Kong this winter is not a local accident. It is a direct, observationally confirmed expression of polar amplification, propagating southward through the atmospheric circulation and reducing the intensity of the East Asian winter monsoon. That is where the regional story rejoins the global one. And it does not stop at Hong Kong. That is the point that needs to be made clearly. The 2-degree warm anomaly over a subtropical coastal city is significant on its own terms, but the same winter told the same story across a broad regional footprint. Stations across Japan recorded departures from normal that clustered in the same direction. Coastal China logged anomalously mild winter conditions across multiple provinces simultaneously. The Korean Peninsula experienced winter temperatures running persistently above climatological expectations. These are not independent anomalies. They form a coherent spatial pattern that stretches across thousands of kilometers of the Western Pacific Rim, a pattern that is the fingerprint of a weakened East Asian winter monsoon, operating at reduced intensity as a system rather than a collection of isolated local weather events. Here is why that spatial coherence matters so much in a scientific context. Individual station records can produce warm anomalies through local effects. A city's urban heat island, a shift in prevailing wind direction affecting a particular valley, a localized oceanic warm pool. But when the same anomaly type appears simultaneously across geographically distinct locations, separated by thousands of kilometers, all sharing a common atmospheric driver, the explanation cannot be local. The explanation has to be systemic. The coherent regional warming from Hong Kong to Seoul to Tokyo to Shanghai in the winter of 2025 to 2026 is a signal of circulation change, not weather randomness. It is the monsoon system itself behaving differently, and it is behaving differently for reasons that trace directly back to what is happening at the pole. Now here is what makes this genuinely important beyond the regional meteorology. The CMIP6 model ensembles, the state-of-the-art climate model generation that informs current IPCC assessments, do project a gradual weakening of the East Asian winter monsoon as Arctic amplification proceeds with continued greenhouse gas forcing. The prediction is there in the literature. What those model ensembles did not consistently produce, at least not in their central projections, was a weakening of this magnitude expressed this clearly in observational records at current global mean temperatures of approximately 1.3 degrees Celsius above pre-industrial. The projected weakening was expected to become clearly detectable at higher warming levels, further into the century under continued emission scenarios. The observational record from this one winter does not by itself prove the models are systematically wrong about the timing. A single season is not a climate trend. But when you place that single season next to the acceleration signal that Foster and Rahmstorf derived from the global temperature record, when you set the Hong Kong data against the simultaneous regional coherence across the Western Pacific Rim, a picture begins to assemble that has a consistent internal logic. The background warming is accelerating faster than models projected. The circulation responses to that warming appear to be manifesting more clearly than models projected at equivalent warming levels. Both signals are pointing in the same direction, and both are doing so ahead of median model expectations. That alignment is not proof of anything in isolation. It is a convergence of evidence that demands examination. and the question it raises, sitting right at the edge of what the current data can answer, is whether what happened to the East Asian winter monsoon in the winter of 2025 to 2026 was an unusually warm season that fell within the range of expected variability, or whether it represents the first clean observational signal of a structural shift in a major atmospheric circulation system. A shift that, if it persists across subsequent seasons and is confirmed by dynamical analysis, would represent a reorganization of the climate system at a scale and timing that changes how we read every other piece of evidence in this investigation. The ocean does not lie. That is not a poetic statement. It is a statement about measurement. The atmosphere is noisy, variable, subject to the kind of short-term fluctuations that make statistical trend analysis a genuine methodological challenge. The ocean is different. It has thermal mass so enormous that it cannot be meaningfully moved by a single season, a single event, or even a single decade of forcing without leaving a record in its temperature structure that is physically unambiguous. When you want to know how much energy the Earth system has actually accumulated, the ocean is not one line of evidence among many. It is the primary ledger, and what that ledger has been recording over the past several years demands the kind of careful, granular attention that the headline temperature numbers alone do not capture. Here is the number that matters most. Approximately 90% of all the excess heat that the planet has accumulated since industrialization began, the net energy imbalance between what the sun delivers and what the Earth radiates back to space, has been absorbed by the world's oceans rather than remaining in the atmosphere. 90%. That fraction is not approximate or contested. It falls directly out of the physics of heat capacity. Water holds thermal energy with an efficiency that air simply cannot match. A column of seawater just a few meters deep contains as much thermal mass as the entire overlying atmosphere. So when greenhouse gases trap energy that would otherwise escape to space, the vast majority of that energy ends up in the ocean, gradually, persistently, building up in the water column over years and decades, rather than expressing itself immediately as the surface air temperature spike that grabs headlines. The practical consequence of this is that ocean heat content measured in units called zettajoules is the physically meaningful metric of planetary energy imbalance in a way that surface air temperature simply is not. Surface temperature is what we feel, what affects weather systems, what biological organisms, including humans, respond to directly. But ocean heat content is what tells you how much energy has actually been committed to the system. And the Argo Float network, a global array of roughly 4,000 autonomous profiling floats that drift through the world's oceans measuring temperature and salinity from the surface down to 2,000 meters depth, has been providing that measurement with increasing precision since the early 2000s. What Argo data through 2025 shows is this. Upper ocean heat content in the 0 to 2,000 meter layer reached record levels for the fourth consecutive year, not approached records, not tied records, reached new records, extending a sequence of annual maxima that now stretches back far enough to constitute a clear, unambiguous trend in the most reliable planetary energy metric we have, and the acceleration in the rate of that heat uptake mirrors, in its timing and its steepness, exactly the atmospheric acceleration that Foster and Rahmstorf identified in the surface temperature record. Stay with me here, because the connection between ocean heat uptake and surface warming acceleration involves a mechanism that is more subtle than it might appear. For most of the industrial period, the ocean absorbed heat not just passively, but efficiently in the sense that the upper mixed layer, the relatively well-stirred surface layer that interacts directly with the atmosphere, transferred a substantial fraction of that heat downward into deeper layers through vertical mixing processes. Thermohaline mixing, wind-driven overturning, eddy diffusion, these processes all move heat from the warm surface toward the colder deep ocean, effectively burying it where it cannot directly warm the atmosphere. The downward transport acted as a buffer. It moderated the rate at which accumulated ocean heat could return to the atmosphere and amplify surface warming. As the upper ocean warms, however, the temperature gradient between surface and deeper water increases, and the density stratification of the water column strengthens. Warmer, lighter water tends to float on cooler, denser water below. As stratification increases, the efficiency of vertical mixing decreases. Heat that would previously have been exported downward stays closer to the surface. the ocean loses some of its buffering capacity at precisely the time the heat load it is managing is at its historical maximum. That physical process, stratification reducing the ocean's capacity to bury heat, is one of the mechanisms connecting the record ocean heat content readings from Argo to the surface warming acceleration in the atmospheric record. But that is not the only connection, not even close. A warmer ocean surface means greater evaporation. That is basic thermodynamics, the rate at which water molecules leave the ocean surface and enter the atmosphere as water vapor increases with surface temperature, following a well-characterized physical relationship. More water vapor in the atmosphere does something specific and important. It adds to the greenhouse effect. Water vapor is itself a potent greenhouse gas. It is responsible, through its role as an amplifying feedback to other forcings, for roughly half of all current greenhouse warming. When the ocean surface warms and evaporation increases, the atmosphere loads up with more water vapor, which traps more outgoing long-wave radiation, which produces additional warming, which further warms the ocean, which drives further evaporation. This is a positive feedback loop, and it is not a theoretical future concern. It is operating now. The specific humidity of the lower troposphere has been measurably increasing in line with the Clausius-Clapeyron relationship across the observational record, and the warming amplification it produces is a known contributor to climate sensitivity. What the current data suggests is that this feedback may be operating at the high end of its estimated range, contributing to the excess residual signal that cannot be accounted for by forcing inputs alone. If you think that is significant, look at what the Atlantic sector of the Argo network has been indicating. Oceanographers analysing the three-dimensional temperature and salinity structure of the Atlantic Ocean have detected something that deserves very careful attention. There appears to be an anomalous reduction in the rate of heat transport from the upper ocean into the deep ocean, specifically in the North Atlantic, a region that is climatically central because it is where the Atlantic meridional overturning circulation performs one of its most critical functions. The Atlantic meridional overturning circulation is a large-scale ocean current system that moves warm, salty surface water northward from the tropics toward the high-latitude North Atlantic, where the water cools, becomes denser, and sinks to depth, flowing southward as a deep cold current before eventually upwelling elsewhere in the global ocean. This overturning acts as a planetary heat distribution system, carrying substantial amounts of thermal energy into the North Atlantic and moderating temperatures across Europe and the northeastern seaboard of North America. It also acts as a pump for deep ocean heat uptake, because the sinking of dense water at high latitudes actively draws surface heat down into the deep ocean and keeps it there. The proxy indicators of overturning strength, including surface salinity patterns in the North Atlantic subpolar gyre, the rate of deep water formation inferred from hydrographic survey data, and fingerprint patterns in sea surface temperature anomalies that oceanographers have developed specifically to detect overturning changes, have been showing a signal consistent with a weakening of this system over the past several decades. The Argo-era data now adds a specific new dimension to that picture. If heat transport from the surface to the deep is slowing in the Atlantic sector, then the deep ocean in that region is becoming less effective at drawing accumulated heat away from the surface layer. That is the same directional effect as the stratification mechanism described earlier, but operating through a different physical pathway. Both reduce the ocean's capacity to buffer surface warming, both are showing evidence of activation in the current observational period, and both would contribute to exactly the kind of acceleration in surface temperature that the Foster-Rahmstorf analysis confirmed in the atmospheric record. This is where the ocean's ledger becomes something more than a record of accumulation. It becomes evidence of a changing relationship between the ocean and the atmosphere. For decades, the ocean absorbed heat and moderated the rate at which that heat returned to the surface. The system was not in balance, it was accumulating energy, but it was managing that accumulation in a way that somewhat dampened the atmospheric expression of the energy imbalance. What the current data suggests is that the management capacity is degrading. Stratification is up. Deep mixing efficiency is down. The Atlantic's overturning may be weakening. The buffer is thinning at precisely the moment the energy load it is managing has reached its highest level in the instrumental record. And water vapor feedback is amplifying the heat that does reach the surface more efficiently than at any prior period in the measurement era. Each of these processes individually would be worth examining. Operating simultaneously and in the same direction, They form a coherent physical explanation for why the atmospheric surface record is accelerating beyond what the forcing inputs alone would predict. The ocean is not hiding the problem anymore, it is returning it. The word tipping point has been used so frequently in public climate discourse that it has nearly lost its technical meaning. It has become rhetorical shorthand for bad things getting worse, a vague gesture toward future difficulty rather than a precise scientific concept. That imprecision matters, because the actual scientific meaning of a tipping point is specific enough to be alarming in ways that the rhetorical version is not. A climate tipping point is not simply a threshold beyond which conditions become unpleasant. It is a threshold beyond which the Earth system component in question, an ice sheet, a forest ecosystem, an ocean circulation pattern, generates its own internal feedbacks that drive continued change independently of whatever external forcing pushed it over the threshold in the first place. Cross that line, and you do not need to keep adding greenhouse gases to keep the change going. The change sustains itself. That distinction between forcing-dependent change and self-sustaining change is the difference between a problem that stops when we stop causing it and a problem that continues even if we do everything right from this moment forward. The acceleration data from Foster and Rahmstorf has forced a reassessment of how close several of these thresholds actually are. Start with Greenland, because the numbers coming off the GRACE-FO satellite gravimetry mission are unambiguous in their direction. GRACE-FO, which stands for Gravity Recovery and Climate Experiment Follow-On, detects changes in the mass distribution of large Earth system components by measuring minute variations in the gravitational field between two spacecraft flying in formation. When the Greenland ice sheet loses mass, the gravitational pull of that region decreases measurably, and the spacecraft separation changes in ways that can be translated into mass loss estimates with remarkable precision. What those measurements showed through 2024 and 2025 was Greenland losing mass at a rate of approximately 280 billion tons per year. That is not a marginal figure. That is enough ice converted to liquid water annually to raise global mean sea level by roughly 3/4 of a millimetre from Greenland alone, each year, compounding onto the previous year's contribution. And the estimate of the warming threshold beyond which Greenland ice sheet loss becomes irreversible, meaning it will continue to completion over centuries regardless of subsequent emissions reductions, sits in the range of 1.5 to 2 degrees Celsius of global warming above pre-industrial levels. We are currently at approximately 1.3 degrees. The margin between present observed warming and that irreversibility threshold is not geological time. It is measured in fractions of a degree that the current acceleration could close within a single human generation. Now look at West Antarctica, and look specifically at Thwaites Glacier, because Thwaites is where the physical stakes become most concrete. Thwaites is sometimes called the Doomsday Glacier in popular coverage, a label that climate scientists find reductive but that reflects a genuine physical reality. It is an enormous glacier draining a significant fraction of the West Antarctic ice sheet into the Amundsen Sea, and its stability is compromised by a geological feature called a retrograde bed slope. Much of the rock beneath Thwaites and the surrounding ice sheet lies below sea level, and the bed deepens as you move inland from the grounding line, which is the point where the glacier transitions from resting on bedrock to floating on the ocean. When relatively warm, circumpolar deep water intrudes beneath the floating ice shelf and melts it from below, the grounding line retreats inland. On a retrograde slope, retreat exposes deeper and deeper ice to ocean contact, accelerating the process in a self-reinforcing loop that does not require any additional warming to continue once it has begun. INSAR radar measurements of grounding line position in the Amundsen Sea sector, made through satellite synthetic aperture radar data, acquired across multiple orbital passes, and difference to detect sub-centimetre surface deformation, show grounding line retreat continuing at rates that exceeded the upper bound of what the IPCC 6th Assessment Report projected as its most aggressive scenario for this region. That is not a detail buried in a technical appendix. That is the edge of a potential marine ice sheet instability, behaving ahead of the envelope our most comprehensive recent assessment defined. And then there is the permafrost. Permafrost is ground that remains at or below 0 degrees Celsius continuously for at least 2 consecutive years. It underlies roughly a quarter of the northern hemisphere land surface, concentrated across Siberia, northern Canada, and Alaska, and it contains an enormous reservoir of organic carbon the compressed remains of plant matter that accumulated over thousands of years under conditions cold enough to prevent decomposition. Current estimates place the total carbon stored in permafrost soils in the range of 1,500 billion tons, which is more than twice the amount currently in the atmosphere as carbon dioxide. When permafrost thaws, that organic matter begins to decompose, releasing both carbon dioxide and methane into the atmosphere. Methane is a particularly potent greenhouse gas, carrying roughly 80 times the warming effect of carbon dioxide over a 20-year comparison window, though it degrades more quickly in the atmosphere over longer timescales. The permafrost carbon feedback, in which warming thaws permafrost that releases carbon that drives further warming that thaws more permafrost, is one of the largest potential amplifying feedbacks in the Earth system. Siberian permafrost monitoring stations recorded methane flux anomalies in the summer of 2025 that exceeded background rates by factors of 2 to 3 in localized hotspots. These are not uniform global numbers. They are concentrated measurements from specific sites, hotspots where thermokarst lake formation and subsurface talc development have created pathways for concentrated methane release. But the factor of 2 to 3 exceedance above background at those sites is the kind of measurement that permafrost scientists track with serious attention, because it suggests localized initiation of the feedback rather than simply gradual diffuse warming of the soil column. Here is where the picture becomes something more than a collection of individual concerning measurements. For decades, climate scientists, including researchers like Timothy Lenton at the University of Exeter, have been developing frameworks for understanding how tipping elements in the Earth system interact with one another. The concern is not simply that individual tipping thresholds might be crossed. The concern is that crossing one threshold generates changes in the Earth system that increase the likelihood of crossing adjacent thresholds, producing cascade sequences that propagate through multiple interacting systems without requiring a corresponding ratcheting up of external forcing at each step. The loss of Arctic sea ice accelerates polar amplification, which weakens the temperature gradient between pole and equator, which affects large-scale atmospheric circulation patterns, which alters precipitation over the Amazon, which interacts with ongoing deforestation to push that ecosystem toward a drought vegetation feedback threshold. These are not speculative cartoon connections. They emerge from dynamical analysis of coupled Earth system models, and the cascade pathways are now well enough characterized to appear in peer-reviewed literature examining tipping element interaction networks. What the acceleration data from Foster and Rahmstorf does to this picture is compress the timeline within which these cascade pathways become relevant. If the effective rate of warming is steeper than previously modelled, the time between consecutive threshold crossings in an interaction cascade shortens. Events that sequential logic might have placed decades apart in a warming scenario, consistent with prior model projections, could be separated by years in a scenario consistent with the observed acceleration. That is not a claim that the cascade has definitively begun. The observational resolution needed to detect an active cascade in its early stages is not something current monitoring networks can provide with certainty. But consider the convergence of what the data is showing right now. Greenland mass loss is running at rates consistent with proximity to its irreversibility threshold. West Antarctic grounding line retreat is exceeding the most aggressive recent model projections. Permafrost methane flux anomalies are appearing at intensities that exceed background by substantial factors in localized but real sites. The East Asian winter monsoon weakened in a manner and at a warming level ahead of median model expectations. The Atlantic meridional overturning circulation is showing proxy signals consistent with reduced overturning strength. Each of these, individually, sits within the range of what physics predicts will happen under continued warming. None of them individually crosses from concerning to definitive confirmation of cascade initiation. But they are not occurring individually. They are occurring simultaneously, against the backdrop of an atmospheric warming signal that has now been confirmed to be accelerating beyond what the models feeding our risk assessments projected. That simultaneity is the question that the data poses, and that the data cannot yet fully answer. The question is whether what we are observing is a collection of independent leading indicators all being pulled forward in time by the same acceleration signal, or whether some of these systems have already begun interacting with one another in ways that are adding their own momentum to the overall picture. The difference between those two interpretations is not academic. One implies that slowing emissions would slow the progression toward each individual threshold at a rate proportional to the forcing reduction. The other implies that some portion of the change already in motion will continue regardless, and that the relevant question is no longer only how much warming we add, but how many cascade linkages are already engaged and carrying their own forward momentum through systems that have operated within narrow boundaries for the entirety of recorded human history. The relationship between a warming planet and its weather is not a metaphor. It is not a simplification for general audiences. It is a direct physical consequence of thermodynamics operating at planetary scale, and the mechanisms that connect background warming to individual extreme events are among the best understood processes in the entire field of climate science. Understanding them precisely is important, because the data coming out of 2025 is not merely consistent with those mechanisms, it is running ahead of them. Start with the most fundamental relationship. The atmosphere's capacity to hold water vapor increases with temperature at a rate of approximately 7% per degree Celsius of warming. This follows from the Clausius-Clapeyron equation, a thermodynamic relationship governing the saturation vapor pressure of water as a function of temperature. It is not a model output, it is physical chemistry. Every degree of warming loads the atmosphere with roughly 7% more potential moisture, and that moisture does not just sit there inertly, it participates. When it precipitates, it releases its latent heat into the surrounding air, intensifying the updrafts that drive storm systems. When it evaporates from a warming surface, it pulls energy away from the ground and stores it in the atmosphere ready to be released elsewhere. The same warming that intensifies rainfall extremes simultaneously intensifies drought by accelerating evaporative demand from soils, vegetation, and surface water. 1 degree warmer does not just mean warmer, it means wetter when it rains, drier when it does not, and more energetic in the transition between the two states. That asymmetry, amplification of both wet and dry extremes simultaneously, is the thermodynamic fingerprint of a warming atmosphere operating exactly as physics predicts. Now layer in the ocean temperature connection. Kerry Emanuel at the Massachusetts Institute of Technology formalized the framework for understanding tropical cyclone intensity in terms of thermodynamics decades ago, developing what is called the maximum potential intensity framework. The concept is relatively intuitive in its essence. A tropical cyclone is fundamentally a heat engine. It extracts energy from the warm ocean surface through evaporation, converts that energy into kinetic wind energy through condensation and updraft dynamics in the storm's core, and exhausts heat at the cold top of the troposphere. The maximum intensity a storm can theoretically reach is constrained by the temperature difference between the sea surface it draws energy from and the upper troposphere it exhausts to. As sea surface temperatures rise, that temperature differential increases, and the ceiling on possible storm intensity rises with it. The storms do not all reach that ceiling. Whether a storm actually approaches maximum potential intensity depends on environmental factors, including wind shear, humidity profiles, and ocean mixed layer depth. But the ceiling itself is rising, and storms that do encounter favourable environmental conditions have more headroom to develop. In 2025, the Atlantic hurricane season put numbers on that theoretical ceiling in ways worth examining closely. Rapid intensification episodes, formally defined as an increase in maximum sustained wind speed of at least 35 knots within a 24-hour period, occurred at roughly double the rate observed in the historical baseline. That is not a single event. That is a seasonal pattern. Rapid intensification is significant beyond the drama of watching wind speeds spike on a forecast track. It has profound practical implications because it compresses the warning time available for evacuation and emergency response. Storms crossing the intensification threshold faster than forecast models project leave coastal communities with less time to act than planning systems assume. The 2025 Atlantic season produced multiple Category 4 and Category 5 landfalling events, where the intensification in the final 24 to 48 hours before landfall substantially outpaced operational model guidance, a pattern consistent with sea surface temperatures providing more thermodynamic fuel than the model climatology underlying those guidance products was calibrated to expect. If you think the ocean-to-hurricane connection is the most straightforward expression of thermodynamic amplification, Look at what happened over the Mediterranean in the same year. The Mediterranean in 2025 experienced what atmospheric scientists are describing as the most geographically extensive simultaneous drought and flood sequence in the observational record for that basin. Not drought in one region and flooding in another, as one might expect from a dipole pattern in precipitation. Drought and flooding occupying overlapping timeframes across subregions, separated by distances that, historically, would place them under quite different weather system influences. The mechanism behind this particular combination involves atmospheric blocking, a phenomenon in which large high-pressure systems become stationary, or nearly stationary, rather than progressing eastward with the normal westerly flow, holding weather patterns fixed in place for days or weeks. A region under the blocking anticyclone receives relentless sunshine and no precipitation. A region at the edge of the block, where the blocked flow is funneled and enhanced, receives repeated slow-moving rain systems that pile up rainfall at rates the ground cannot absorb. The connection between blocking frequency, duration and background warming operates through the jet stream, the band of strong upper-level westerly winds that encircles the globe in the mid-latitudes and steers surface weather systems. The jet stream's behaviour is governed in part by the temperature gradient between the tropics and the Arctic. As the Arctic warms faster than the tropics, that gradient weakens. A weaker temperature gradient produces a jet stream that is less energetic and more prone to large amplitude meanders, deviating far to the north and then far to the south in wave patterns that can lock in place and stall. When those waves stall, weather systems stop moving. Blocking events become longer and more intense. The connection is active scientific debate at its margins. Not all researchers assign equal weight to the Arctic jet stream linkage, but the observational pattern from 2025, extended blocking driving simultaneous drought and flood extremes at historically unprecedented geographic extent across the Mediterranean, is directionally consistent with what that mechanism would produce. Here is where it gets important to pay close attention to the attribution science, because that is where the data becomes most revealing about the gap between what models predict and what the real world is producing. Attribution science has matured over the past 15 years from a theoretical framework into an operational methodology. Using large ensembles of climate model simulations, researchers compare the probability of a specific extreme event occurring in a world with current greenhouse gas concentrations against the probability in a counterfactual world without human forcing. The ratio of those probabilities is the probability ratio, and it is the primary metric for answering the question of how much more likely human warming made a particular event. These analyses are now performed rapidly enough that attribution assessments for major events are sometimes published within weeks of the event itself. What the attribution analyses for major extreme events in 2025 are showing is a consistent pattern that demands explanation. The probability ratios, the factor by which human warming increased the likelihood of specific events, are coming in above the values that the model ensembles underlying those analyses would project for the current level of global mean warming. In plain terms, the real world is producing extreme events that are more intensified relative to baseline than the model ensemble at the same warming level predicts they should be. This is a direct parallel to the core finding of Foster and Rahmstorf at the global mean temperature level, except it is showing up not just in the trend statistics but in the physical behaviour of individual extreme weather systems. The atmosphere is not just warming faster than models project, it is amplifying extreme events faster than those models project at equivalent warming levels. The question that immediately follows from that parallel is whether it represents the same underlying gap, whether the same set of processes that are producing the acceleration in the mean temperature signal, the unmasked aerosol suppression, the positive low cloud feedbacks, the reduced oceanic buffering, are simultaneously producing larger than expected extremes through the Clausius-Clapeyron, amplification, and maximum potential intensity pathways. The physical logic connects them. A warmer lower troposphere loaded with more water vapour intensifies precipitation extremes faster per unit of surface warming. A higher sea surface temperature ceiling on maximum potential intensity allows more storms to reach intensities that models calibrated to prior climate states underestimate. The feedback mechanisms that are accelerating the mean are likely also accelerating the tails of the distribution. The mean and the extremes are coupled through the same thermodynamics, and if the mean is running ahead of predictions, the extremes running ahead of predictions is not an independent anomaly. it is the expected consequence of the same underlying gap. What that means in practice is this. The standard approach to disaster risk assessment for extreme weather uses model ensembles calibrated to historical climate behaviour and then projected forward under emission scenarios. Infrastructure design standards, insurance actuarial tables, emergency management protocols, coastal zoning regulations, all of these draw from probability estimates derived from those models. If the models are systematically underestimating the amplification of extremes at current warming levels, then every risk estimate built on those models is operating with inputs that are lower than the physical reality justifies. The underestimation is not random noise, it is directional, and it is appearing not in projections for future warming levels, but in attribution analyses for events that are happening now. The gap between what models say and what the real world is doing is not a future problem to be managed with better projections. It is a present condition already expressing itself in the infrastructure of weather risk that societies have built their planning assumptions around. The gap between what our models say and what the physical world is actually doing has now grown large enough that it demands an explanation. Not a reassurance, not a technical footnote about uncertainty ranges, a genuine, mechanistically grounded explanation. And that is where the scientific community currently finds itself in a position that is unusual in its structure. There are several competing hypotheses, each supported by real observational evidence, each individually plausible, and each pointing toward a somewhat different picture of what comes next. The fact that more than one explanation fits the data is not a reason for comfort. It is a reason to examine each of them with more care than a single tidy answer would require. The first hypothesis, and in some ways the most empirically tractable of the three, centres on maritime shipping emissions. Follow this carefully, because the mechanism is counterintuitive the first time you encounter it. For decades, the global merchant fleet burned high sulfur fuel oil as its primary energy source. Combustion of that fuel released sulfur dioxide into the lower atmosphere over the world's major shipping lanes, and that sulfur dioxide reacted with atmospheric water and oxygen to form fine sulfate particles. Those particles scatter incoming sunlight back towards space. They also act as cloud condensation nuclei, increasing the reflectivity of low marine clouds over the shipping corridors. The net effect was a persistent geographically concentrated cooling influence across the major ocean routes, particularly in the North Atlantic and North Pacific. It was in effect an inadvertent geoengineering program conducted by global commerce, and it had been suppressing surface temperatures over those regions for decades, without anyone having designed it to do so. In January 2020, the International Maritime Organization implemented its 2020 sulfur regulations, requiring ships to switch to very low sulfur fuel. Compliance was rapid and widespread. Within months, sulfur dioxide emissions from the global shipping fleet dropped dramatically. The aerosol veil over the shipping lanes began to thin, and the cooling effect those aerosols had been providing began to lift. Gavin Schmidt and colleagues at NASA's Goddard Institute for Space Studies have argued that this aerosol unmasking effect could account for somewhere in the range of 1/10 to 2/10 of a degree Celsius of additional warming since 2022, as the suppressed warming from decades of aerosol loading was revealed beneath the lifting veil. That is not a trivial number. Against a background warming trend that has itself been measured in tenths of a degree, 1/10 to 2/10 is a contribution large enough to meaningfully compress the gap between model projections and observed acceleration. Stay with me here though, because this explanation, while real and quantitatively significant, does not fully close the gap on its own. The aerosol unmasking effect is concentrated geographically over the shipping lanes, and while it propagates somewhat into adjacent regions through atmospheric circulation, it does not have a uniform global footprint. The Foster and Rahmstorf acceleration signal is global in character, showing up in the residual after regional and natural variability has been removed across the full planetary temperature record. Aerosol unmasking is a contributor. The current evidence suggests it is probably not sufficient by itself to account for the full magnitude of the excess residual signal. That brings us to the second hypothesis, which involves clouds, specifically the behavior of a low marine stratocumulus clouds over the subtropical ocean. If you want to locate the single largest remaining source of uncertainty, in estimates of how sensitive the climate is to a given increase in greenhouse gas forcing. This is it. Low marine stratocumulus clouds are extensive, persistent sheets of cloud that form in the lower troposphere over relatively cool ocean water in the subtropics, particularly in the eastern Pacific and eastern Atlantic, where cold, upwelling brings cooler water to the surface. These clouds cover enormous areas, and because they are bright relative to the dark ocean surface beneath them, they reflect a substantial fraction of incoming solar radiation back to space. They have a strong cooling effect. The question that has bedeviled climate science for decades is how the coverage and reflectivity of these clouds changes as the ocean beneath them warms. If warming reduces their coverage, the ocean surface loses a reflective shield, absorbs more solar radiation, and warms faster. That is a positive feedback, meaning it amplifies rather than dampens the warming. If warming increases their coverage, the reverse is true. What the CIRRUS satellite instrument, the clouds and the Earth's radiant energy system operated by NASA, has been recording since 2020 is a measurable decrease in low cloud cover over the eastern Pacific and eastern Atlantic. The reduction is not enormous in absolute terms. We are talking about fractional decreases in cloud fraction across specific ocean regions. But the implications for the planetary energy balance are not small. A decrease in low marine stratocumulus coverage allows more solar radiation to reach the ocean surface, and because these clouds cover such vast areas, even modest fractional reductions translate into meaningful additional energy input at the global scale. Researchers analysing the CIRRUS record have calculated that the observed reduction in reflected solar radiation, the so-called Earth Energy Imbalance signal, derived from top-of-atmosphere measurements, increased measurably after 2020 in a way that is consistent with the magnitude and timing of the surface temperature acceleration. The cloud feedback, in other words, appears to be operating at the high end of the range that climate models have historically assigned to it, and doing so earlier than central model projections suggested it would. This is significant in a specific technical sense. Climate sensitivity, the amount of equilibrium warming expected from a doubling of atmospheric carbon dioxide, has a central estimate around 3 degrees Celsius, but carries an uncertainty range extending from roughly 2.5 to 4 degrees in the most recent IPCC assessment. The lower end of that range was, in part, supported by the apparent behaviour of low cloud feedbacks in observational analyses of the recent past. If the CERES data is now showing that low cloud coverage is declining in response to current warming at the high end of modelled uncertainty ranges, that observation pulls the effective climate sensitivity estimate upward toward the higher end of its uncertainty range. And if the effective climate sensitivity is closer to 3.5 or 4 degrees than to 3, then the implied remaining carbon budget for any given temperature target is substantially smaller than IPCC central estimates, and the acceleration in warming relative to prior projections becomes physically coherent without requiring any exotic new mechanisms. Here is where the third hypothesis enters, and this one occupies a different position on the spectrum of scientific consensus. A relatively small but scientifically credible group of atmospheric chemists has been examining whether changes in the stratosphere, specifically in the background level of stratospheric aerosols and in upper tropospheric ozone chemistry, might be altering the energy balance at the surface through dynamical pathways that standard general circulation models do not represent with adequate fidelity. The argument, developed in several peer-reviewed papers, though not widely adopted in the mainstream modelling community, runs roughly as follows. Stratospheric aerosol background levels, meaning the diffuse layer of aerosol that persists in the absence of major volcanic eruptions, have been declining gradually since the relatively volcanically active period of the 1980s and 90s. A lower background aerosol level means slightly less scattering of solar radiation in the stratosphere, which means marginally more solar energy reaching the troposphere. The magnitude of this effect is estimated to be small, on the order of a few hundredths of a watt per square metre, but it is a forcing term that sits outside the standard aerosol forcing inventories used in general circulation model baseline runs. The dynamical component of the hypothesis is more complex and more contested. Changes in stratospheric temperature gradients, whether from aerosol changes or from trends in stratospheric ozone distribution, following the recovery of the ozone layer under the Montreal Protocol, can in principle affect the strength and structure of the stratospheric polar vortex. The polar vortex in turn influences tropospheric circulation through downward propagation of stratospheric anomalies, a pathway that affects jet stream behavior, blocking frequency, and surface temperature patterns in the mid-latitudes. Whether this pathway is contributing meaningfully to the observed acceleration in surface warming, and whether its magnitude is large enough to be detectable against the background of the other forcing changes under discussion, remains genuinely unresolved. The research exists, it is peer-reviewed, it is not consensus, and it identifies a class of mechanism that current general circulation models may represent imperfectly, which means it cannot simply be dismissed on the grounds that models do not show a large effect. What you end up with when you place all three hypotheses side by side is not a clean verdict. Aerosol unmasking from shipping regulations is real, quantitatively supported, and probably accounts for a portion of the acceleration. Low cloud feedback operating at the high end of modelled uncertainty ranges is observationally supported by the series record and provides a physically coherent mechanism for elevated effective climate sensitivity. Stratospheric dynamical pathways represent a plausible but not yet quantified forcing channel that may be adding an unrepresented term to the planetary energy budget. The honest scientific position is that the acceleration likely reflects more than one of these operating simultaneously, and that the compounding of multiple high-end outcomes across the uncertainty ranges of several different processes is itself a signal about how risk should be characterized. Not one extreme outcome in one area, but multiple high-end outcomes activating at the same time and in the same direction. The question that sits at the end of all three hypotheses is whether a combination of partially understood, overlapping processes is sufficient to fully close the model observation gap, or whether the gap is large enough that something else, something not yet clearly articulated in the peer-reviewed literature, is also contributing. That question does not have an answer yet, but the policy world is being asked to make trillion-dollar decisions while it remains open. The number that should anchor every climate policy conversation happening anywhere on Earth right now is not 1.3 degrees, it is not 1.5 degrees, it is 37 billion. That is the approximate number of tons of carbon dioxide that human civilization is currently emitting into the atmosphere every single year, and it is the number against which every other figure in the policy calculus has to be measured. Because here is what the acceleration data has done to the arithmetic that underlies the entire international climate framework. It has not simply made the problem more urgent in a general sense. It has potentially invalidated the specific numerical foundations on which every formal climate commitment currently in existence was calculated. Let me walk you through exactly how that works, because the mechanics matter. The Paris Agreement, signed in 2015 and now ratified by nearly every nation on Earth, set temperature targets of 1.5 and 2 degrees Celsius of warming above pre-industrial levels as the thresholds to aim for. To operationalize those targets, climate scientists developed the concept of a carbon budget. A carbon budget is exactly what it sounds like. It is the total cumulative quantity of carbon dioxide that can be emitted globally, while still giving the planet a reasonable probability of staying below a specified temperature threshold. The budget is finite. Every ton emitted draws it down. When the budget is exhausted, the temperature threshold is effectively committed to. The logic is clean and the accounting is relatively tractable, which is partly why the framework became so central to international negotiations. Here is where the problem enters. The carbon budget estimates published in the IPCC 6th Assessment Report were calculated using an equilibrium climate sensitivity value, centered around 3 degrees Celsius per doubling of atmospheric carbon dioxide, with associated transient climate response estimates that govern how quickly warming accumulates along an emissions trajectory rather than at theoretical equilibrium. Those central values produced carbon budget estimates for a likely chance of staying below 1.5 degrees of warming in the range of roughly 400 to 500 billion tons of carbon dioxide remaining from a baseline year of 2020. Stay with me here, because the arithmetic that follows from this is important. At current emissions of approximately 37 billion tons per year, a budget of 400 to 500 billion tons implies roughly 11 to 14 years of remaining budget at present rates. That is already a narrow window, but now layer in what the acceleration evidence suggests about effective climate sensitivity. If the positive low cloud feedback operating at the high end of modelled uncertainty ranges is genuinely engaged, if the effective climate sensitivity during the current acceleration period is closer to 3.5 or 4 degrees, than to the central estimate of 3, then the carbon budget estimates derived from the central sensitivity value are not conservative approximations with comfortable margins. They are overestimates. The remaining budget at a sensitivity of 3.5 to 4 degrees is not 400 to 500 billion tonnes. It is more plausibly in the range of 200 to 300 billion tonnes. At 37 billion tonnes of annual emissions, that budget runs out in 5 to 8 years from the present. That is not a projection for the middle of the century. That is a window that closes before the decade does. Think about what that actually means in terms of the policy architecture that currently exists to address it. Every nationally determined contribution submitted under the Paris framework, the specific emissions reduction commitments that each country has made as its part of the collective effort, was designed against the prior budget estimates. The ambition levels, the timelines, the sectoral targets, the financing mechanisms, all of them were calibrated to a budget that the acceleration data now suggests may be significantly more generous than the physical reality justifies. This is not a marginal recalibration. If the budget is roughly half of what the central estimates suggested, then every current nationally determined contribution that was designed to be consistent with a 1.5 degree pathway under the prior budget calculation is now, under the revised budget implied by the acceleration evidence, a contribution consistent with exceeding that threshold, not approaching it at the limit, exceeding it, potentially substantially, depending on how much the effective sensitivity has shifted. Now bring in the energy transition picture, because that is where the policy tension becomes fully visible. Solar and wind capacity additions reached record levels in 2024 and 2025, with more than 500 gigawatts of combined new generation capacity installed globally across those 2 years. That number is genuinely significant. The renewable build-out is real, it is accelerating, and the cost curves for solar photovoltaics and onshore wind have dropped faster than nearly any projection from a decade ago anticipated. These are not trivial achievements. They represent the largest and fastest energy technology deployment in industrial history. And they are still not enough. Not at current rates. Not against the demand trajectory that is simultaneously expanding on the other side of the ledger. Total global energy demand has continued rising, driven by electrification of transport and heating, by the explosive growth in power consumption from artificial intelligence data center infrastructure, and by legitimate development needs in the global south where hundreds of millions of people are accessing electricity and modern energy services for the first time. The consequence is that while the share of renewable energy in the global electricity mix has grown substantially, total fossil fuel combustion has not entered the steep, sustained decline that the physics of the carbon budget requires. It has plateaued. Plateau is not reduction. Plateau means the budget continues drawing down at roughly the same rate it has been, and the revised budget implied by the acceleration evidence has less capacity to absorb a prolonged plateau than the prior estimates did. Look at the carbon capture numbers, because they complete the picture. Direct air capture technology, which pulls carbon dioxide directly from ambient air using industrial processes, is the only currently demonstrated approach that can reduce atmospheric carbon dioxide concentrations rather than merely slowing their increase. Its operational capacity as of the current period stands at roughly 1/10 of 1 million tonnes per year globally across all existing facilities. The need, under any scenario where the emissions gap between current trajectories and required reductions is to be bridged even partially by carbon removal rather than solely by emissions cuts, is measured in billions of tonnes annually. The gap between those two numbers, between 1/10 of 1 million tonnes and several billion tonnes, is not a gap that learning curves and scale economics can close in a time frame relevant to the carbon budget clock. Direct air capture is not ready to carry the load that optimistic modelled scenarios have often assigned to it, and that gap in the mitigation portfolio means a larger fraction of the required work has to be done through direct emissions reductions, which in turn means the policy demands on every other sector of the economy become correspondingly more stringent. Here is where the structural problem with the international negotiation framework comes fully into view. The Conference of the Parties process, the COP framework under which the Paris Agreement has been operationalised, was designed as an iterative mechanism for increasing ambition over time. Countries submit commitments, those commitments are reviewed, and every 5 years the framework calls for updated contributions that ratchet ambition upward. the entire architecture assumes that the fundamental scientific baseline against which those ambitions are calibrated remains relatively stable between assessment cycles, shifting at the pace of formal IPCC assessment reports, which emerge on roughly 6 to 7 year cycles. The acceleration finding from Foster and Rahmstorf does not fit that pace. It is a 2026 result suggesting that the budget arithmetic in the 2021 Sixth Assessment Report is already potentially obsolete in the direction of being too permissive. The mechanism for incorporating that update into the formal policy framework does not operate at the speed the physics appears to be moving. What this creates, when you hold the acceleration data against the energy transition progress and the carbon capture reality simultaneously, is a situation that goes beyond urgency in the conventional sense. It is a situation where the measurement of the problem is moving faster than the institutional architecture designed to respond to it was built to accommodate. The question that sits at the end of this is genuinely uncomfortable. If the carbon budget estimates derived from pre-acceleration science are now insufficient guides for the ambition levels required, and if the institutional revision cycle for updating those guides operates on a timeline that the physical situation is outrunning, then the next COP faces not an ordinary question of whether participating nations should commit to more aggressive targets. It faces a prior and harder question: whether the quantitative foundations of the commitments being negotiated accurately reflect the physical system those commitments are meant to manage. That is a different kind of conversation than any COP has yet been required to have, and the data that forces that conversation is not in dispute. The investigation has now crossed every major piece of terrain available to it: the atmospheric record, the ocean heat ledger, the regional circulation anomalies, the ice sheets and permafrost, the extreme weather attribution gap, the competing mechanistic hypotheses, the policy arithmetic. Each of those domains, examined individually, produces a concerning picture. Examined together, with the internal logic connecting them made explicit, they produce something more than a collection of concerning pictures. They produce a coherent account of a physical system whose response to human forcing has shifted, not toward new physics, not toward any violation of thermodynamic principles, but toward the simultaneous early engagement of multiple feedback processes that were always predicted to activate, and that are now doing so in a synchronized manner that the models feeding our risk assessments did not project at this level of warming. Let me give you the full synthesis directly. The core anomaly introduced at the beginning of this investigation was deceptively straightforward to state, but genuinely difficult to explain. After removing every quantifiable natural forcing term from the global temperature record, the residual anthropogenic signal was steeper than the measured forcing inputs should theoretically produce under standard climate sensitivity assumptions. That gap, confirmed at over 98% statistical confidence, was not an artifact of a single bad dataset or a single methodological choice. It survived rigorous decomposition. It survived the removal of two of the most powerful El Nino events in the modern record. It survived careful treatment of volcanic aerosol and solar irradiance terms. What remained was a real signal, and its magnitude exceeded the expectation built into our best predictive frameworks. The resolution of that anomaly, as the full body of evidence now indicates, does not hinge on a single missing mechanism hiding in some unexplored corner of atmospheric physics. That would be a tidier story. It would be easier to communicate and easier to act on. What the data actually shows is messier, and in some ways more difficult to absorb. The gap is explained by several processes operating simultaneously, each at or near the high end of its individually estimated uncertainty range, and their contributions compounding in the same direction at the same time. Aerosol unmasking from the reduction in maritime shipping sulfur emissions removed a cooling veil that had been suppressing surface temperatures for decades over the major ocean routes. Low marine stratocumulus cloud coverage has been declining over the eastern Pacific and eastern Atlantic, in a pattern consistent with a positive cloud feedback operating at the upper end of the range that climate sensitivity estimates bracket. Upper ocean stratification has increased as the mixed layer warms, reducing the efficiency of vertical heat export to depth. The Atlantic meridional overturning circulation is showing proxy signals consistent with reduced strength, diminishing one of the ocean's primary mechanisms for exporting surface heat into the deep. water vapor feedback is amplifying each increment of surface warming at a rate that scales with the temperature-dependent physics of evaporation and atmospheric moisture capacity. And methane flux from permafrost systems is appearing in localized but real measurements at intensities that suggest the earlier stages of carbon release ahead of median projected timelines. None of these individually closes the full gap between observed acceleration and prior model projections. But here is what matters. The gap does not require any single process to close it entirely. It requires several processes, each of which the evidence supports as active and operating in the direction the physics predicts, to be contributing simultaneously. And when you sum a conservative estimate of the aerosol unmasking contribution, a cloud feedback contribution consistent with the high end of the Ceres-derived observational record, a reduced oceanic buffering contribution from both stratification and overturning slowdown, and an early permafrost methane signal at the magnitudes the monitoring stations are recording, the total is sufficient to account for the excess residual signal without invoking any mechanism outside current physical understanding. The planet is not behaving as though the rules have changed. It is behaving as though the rules are playing out faster than the central tendency of our model ensemble predicted, with multiple high-end outcomes from different physical subsystems activating in the same decade, rather than being distributed across different warming levels separated by decades of further forcing. Stay with me here, because this distinction carries a specific and important implication. When forecasters and risk analysts talk about model uncertainty, the implicit assumption underlying how that uncertainty is typically communicated is that high-end outcomes from different uncertain processes are not correlated with each other. That is, the chance of getting high-end cloud feedback and high-end ocean stratification change and high-end permafrost response all at the same time is much smaller than the chance of getting any one of them individually at its high end. The probability of coincident extremes across independent uncertain processes is small. That assumption of low correlation between high-end outcomes is part of why the central estimate of climate sensitivity has historically been treated as a reasonable central planning assumption for policy, rather than the lower-end probability distribution being used as a guide. What the current data record is empirically demonstrating is that the correlation between high-end outcomes across different subsystem feedbacks may be higher than the independence assumption implies. The processes may be coupled to one another. Reduced sea ice drives Arctic amplification, which weakens the temperature gradient which affects jet stream behavior, which influences cloud distribution, which affects surface energy balance, which feeds back to ocean temperature, which modulates ENSO amplitude, which complicates the very decomposition used to isolate the human signal. These are not cleanly independent processes drawing from separate probability distributions. They are interacting components of a single coupled system, and when one moves toward its high end, it perturbs the others in ways that tend to pull them toward their own high ends as well. The coincidence of multiple high-end outcomes simultaneously is therefore not the statistical improbability it would appear to be if the processes were independent. It may be the expected behavior of a coupled system where positive interactions between feedback processes create a systematic tendency for high-end outcomes to cluster. That is the real answer to the question this investigation began with. The models did not fail to predict the acceleration because they were missing one hidden mechanism. They underestimated the degree to which multiple known mechanisms would engage coherently and synchronously, amplifying each other through the coupling structure of the Earth system, at warming levels below what median projection suggested would be needed to activate them. The acceleration is not anomalous. It is, on reflection, physically coherent. It is simply occurring along the upper tail of the distribution of possible outcomes, rather than near the middle of it. And it is occurring now, not in a future scenario envelope, but in the observational record being produced by instruments operating today. Think about what that actually means for the urgency calculus. In a system where feedbacks are behaving closer to their high-end estimates, every additional ton of carbon dioxide added to the atmosphere commits a large increment of future warming than the central sensitivity estimate would imply. Every year of emissions at current rates draws down a carbon budget that is plausibly narrower than the figures most policy documents are currently using, and the physical consequences already in motion, the ice sheet mass loss running ahead of projections, the grounding line retreat in West Antarctica exceeding the most aggressive IPCC scenario boundaries, the monsoon circulation weakening expressing itself in full seasons of observational data rather than just model output. These are not signals that stop responding to further forcing just because their current trajectory already exceeds expectations. They continue responding, and under a high-end feedback regime, they respond more per unit of additional forcing than median estimates would suggest. The scientific case this data makes is therefore not simply that intervention is necessary, which has been established for decades. It is that the cost of each unit of delay is higher now than it was when the prior projections were the best available guide, not linearly higher. The compounding nature of reinforcing feedbacks means that the physical consequences accumulating per year of delay are larger than the consequences that accumulated per year of delay in the period when the Earth system was operating closer to its median projected behaviour. The urgency is not the same urgency it was 5 years ago, stated more loudly. It is a structurally different urgency, one where the feedback processes that amplify the problem are measurably more engaged than they were, and where the window between current warming and the thresholds beyond which self-sustaining changes become the dominant driver of the trajectory is narrower in physical time than carbon arithmetic alone communicates. That is what the data is saying, not loudly, with precision. And precision, in this case, demands to be heard.